I recently covered Lockheed Martin in a Space News video on their VSAT technology, vertical solar panels for deployment near the south pole of the moon. It turns out they have a whole lunar architecture plan which they detail in a 32-page PDF document. It's actually written as a novella from the point of view of a commercial lunar contractor living on the moon in 2044. For those interested, a link to this document is in the video description. In this video, I'll go over their vision of a water-based lunar architecture on the moon. This plan dovetails with space startups such as iSpace and Argospace, which also envision water powering a cislunar ecosystem. Any sustainable lunar architecture will consist of space startups, large commercial companies and national space agencies, and the 54 countries which have signed the Artemis Accords, so it pays to understand how these large companies like Lockheed Martin think about our future on the moon and in cislunar space. Before we explore their vision, let's first explore what Lockheed Martin is currently working on as part of the Artemis program to return to the moon in a sustainable way. Lockheed Martin plays a crucial role in the Artemis program. They are the prime contractor for the Orion spacecraft that astronauts use to travel to lunar orbit. Once in orbit around the moon, astronauts will transfer to one of the two human landing systems selected by NASA, either Starship or the Blue Origin lander. After their mission on the moon finishes, they will rendezvous with Orion and return back to Earth. Lockheed Martin will also provide the cislunar transporter, which transports hydrogen and oxygen from low Earth orbit out to the moon to refuel the Blue Origin lander. As mentioned, their VSAT technology will provide power to habitats, rovers and equipment near the South Pole. They are partnering with Blue Origin on long-term storage of cryogenic propellant to support refueling of spacecraft and lunar landers. Let's now look at Lockheed Martin's vision. They say in their preamble that the best lunar architecture is water-based, nuclear-enabled and commercially invested. Their vision is not based on any one company or nation, it's a vision for all companies, nations and partners. In situ resource utilization, or ISRU, living off the lunar land. To achieve sustainable lunar exploration, we must harness the moon's local resources by extracting and processing them into essential materials. This approach, known as in situ resource utilization, is critical to reducing the costs of maintaining a long-term human presence on the moon. Without cost-effective solutions, the Artemis program risks facing cancellation, much like the Apollo program in the 1970s. The moon offers a wealth of resources that can be harvested and transformed into valuable products, including water, hydrogen, oxygen, helium-3 and industrial metals. Additionally, silicon found in lunar rocks can be used to manufacture solar panels. For instance, Blue Origin has successfully demonstrated the production of solar panels using lunar silicon, paving the way for large-scale solar farms to generate abundant power during the lunar day, which lasts for 2 weeks. Lunar soil or regolith is another versatile resource. It can be processed and hardened to create construction materials for roads, landing pads and habitation modules. Startups like Icon and Ethos Space Resources are already developing technologies to build lunar infrastructure using regolith, minimizing the need to transport heavy materials from Earth. Water, the essential resource for lunar operations. Water is the cornerstone of sustainable lunar exploration. It's the moon's most critical resource. As Timothy Sitchin, Lockheed Martin's lead space exploration architect, explains, water is an amazing resource for space exploration and is found throughout the solar system, including in the moon's polar craters. If we can avoid launching propellant from Earth for these missions, sustainable space exploration is much more feasible. In a sense, water could be rocket fuel, unquote. Harnessing lunar water. To tap into lunar water, exploration begins with prospecting. Rovers and drills bore into the subsurface, sampling materials in promising locations like the South Pole's permanently shadowed craters. Using data from these efforts, scientists create 3D models to map ice concentrations and depths, converting estimated resources into proven resources with economic value. Once viable ice deposits are identified, excavation and processing facilities extract and purify water. Space startups can attract investment by securing contracts with NASA or other agencies, guaranteeing annual purchases of lunar water, incentivizing rapid development of extraction technologies. Water-powered transportation. Water drives transportation across the inner solar system, powering missions to the Moon, Mars, and beyond. For slow and simple transport, asteroid mining spacecraft heat water into steam. It's low cost and low speed, providing a simple way of moving mining materials into cislunar space. For faster and more powerful transportation, lunar water can be split into liquid hydrogen and oxygen using electrolysis. For top-of-the-line performance, for instance transporting crew to Mars, nuclear thermal propulsion using hydrogen from lunar water ice can be used. The cislunar economy can use lunar water ice to refuel spacecraft and lunar landers with water-derived propellant. This spreads construction costs over multiple missions, reducing recurring expenses and increasing sustainability. Let's be clear, there are challenges handling liquid hydrogen. Its ultra-low density requires complex management systems needed to prevent boil-off, with the energy-intensive processes needed for purification, electrolysis and liquefaction are expensive. But these are all non-recurring costs. Once you have developed the tech, you have a reliable system to store large amounts of liquid hydrogen to power the cislunar economy. Sustainability hinges on reducing reliance on Earth-based supply chains. Water, abundant in lunar craters, frozen asteroids, Martian poles and subsurface glaciers, eliminates the need to launch propellants from Earth. As technologies mature, innovations like high-performance cryocooling, zero boil-off storage and no-vent filling will further lower transportation costs. By leveraging water for life support, propulsion, power and shielding, lunar operations can thrive. With continued investment in ISRU, the inner solar system will run on water, enabling a permanent, cost-effective human presence on the Moon and beyond. Nuclear fission. Lockheed Martin is a big believer in the power of nuclear fission power, both for generating electric power on the surface of the Moon and also to propel spacecraft to the Moon and onto Mars. Nuclear fission provides a lot of energy in a small package, and it doesn't matter whether the sun is shining. This means high thrust and high efficiency for nuclear thermal propulsion and constant power day or night for the Moon and Mars. Solar power has many benefits, especially near the South Pole, where the sun shines 80 to 90% of the time. It's great for bootstrapping a small base given its low cost, simplicity, lack of moving parts and the maturity of the technology. But with larger bases and more fixed infrastructure, the benefits of nuclear fission become obvious. With intermittent power, battery storage is needed. Batteries are heavy and don't have good performance in cold conditions such as a lunar night. For instance, lithium batteries lose 20 to 30% of their capacity at minus 20 degrees C. During the lunar night, temperatures plunge to minus 173 degrees C for 2 weeks. The electrolytes would freeze or crack under those temperatures, meaning heating would have to be supplied throughout the lunar night to keep them functioning. To survive the lunar night, massive battery farms would be needed, far exceeding current capabilities, and would be very heavy to transport. Solar panels and battery storage are a poor solution for anything other than a temporary base. Nuclear fission is the obvious choice for large continuous supply of power throughout the lunar day and night. Solar panels don't work in craters, which are scientifically the most interesting locations and where water ice is most likely to be found in commercially exploitable amounts. Power beaming could work, but becomes less efficient over distance, which would be a problem for large craters like Shackleton. Fission, on the other hand, generates power wherever you place it. The fuel uses low-enriched uranium encased in pellets, so it's safe to use and handle. In addition, reactors can be shielded with regolith. Habitation. Initially, living modules will likely be hard-shell habitats, similar to the International Space Station modules. More effective habitats, however, are likely to be inflatable, as they can have much larger internal volumes and arrive flat-packed. The fabric of these inflatable habitats is actually tougher than metallic modules. Once lunar excavation and in-situ resource utilization is started, the habitat modules can be covered with regolith to provide extra protection against solar flares and radiation. Printing habitats using processed regolith is also possible in the future. In addition, discovered lava tubes can be investigated as they provide protection from radiation and buffer thermal swings from the lunar day-night cycle. Studies have shown that the temperature inside a lava tube on the Moon would remain relatively constant at minus 20 to minus 30 degrees centigrade. That's minus 4 to minus 22 degrees Fahrenheit, as a rock acts as a thermal buffer. This reduces the energy needed for habitat climate control, compared to surface structures exposed to extreme temperature fluctuations. Some lava tubes could be cavernous, with large internal volumes providing plenty of extra storage or possibly supporting an entire base. Recent studies confirm lava tubes in various lunar regions. Lunar Surface Propellant Station. As the number of lunar missions increases, establishing propellant storage facilities on the Moon's surface makes sense. Hydrogen is difficult to keep cold over a long period of time. Why not use the Moon's surface for this job? Mass is not a problem on the surface, unlike in lunar orbit. All that mass can be used to do one job efficiently: keep liquid hydrogen cold for a long period of time. Transporters can be optimized for quickly moving cryogens from source to destination with minimal boil-off. Offloading a lot of the tech required for long-term storage onto a surface facility where mass doesn't matter and power is available in large amounts keeps the transporter lighter and more efficient. Lunar Power Grid, powering the Moon's future. Power is essential for every operation on the lunar surface. Generated power comes in many different forms at different locations, times and qualities, and voltage and current levels. With all different types of equipment in use requiring different voltages, it's important to have a power grid that can step up or step down the voltage to supply each piece of equipment with the correct voltage. At the lunar South Pole, vertical solar panels mounted on crater rims, such as a Shackleton connecting ridge, track the near-constant sunlight. Regenerative fuel cells, powered by hydrogen and oxygen from lunar water, offer portable or backup power for rovers and temporary setups. Compact nuclear fission reactors provide steady, high-output power unaffected by the 14-day lunar night. Ultra-high voltage cables crisscross the lunar surface, connecting power sources to habitats, processing facilities, and microgrids. These cables form the grid's backbone, distributing energy efficiently across the rugged terrain. In flat, open areas, wireless optical beaming systems transport power, reducing the need for physical cables and simplifying deployment in challenging landscapes. At the bottom of permanently shadowed craters, especially the larger ones like Shackleton crater, fission reactors at the base of the crater make the most sense. The lunar grid links all these different types of power generation into a seamless whole, monitors the supply, diverting extra power to storage systems such as fuel cells or batteries during peak production. When demand spikes, stored energy is routed to peak usage terminals, ensuring uninterrupted operations. For more on lunar power grids, check out my video on a space startup building DC to DC microgrids for the Moon. The company is called Orbital Mining Corporation. Electromagnetic Launch. One piece of tech that doesn't get mentioned often is an electromagnetic launch system for the Moon. This could revolutionize the efficiency of cislunar transportation by cheaply launching lunar resources into orbit. This system uses electromagnetic force to accelerate containers of water and cryogens to orbital velocities. With the Moon's low gravity, only 1/6 of the gravity of Earth, and no atmosphere, what would be impractical on Earth is easily achievable on the Moon. A catcher element in lunar orbit aggregates each arriving container. From there, the resources are transferred to an orbiting propellant station. Instead of burning precious propellant to move resources off the Moon, use electrical power from solar panels and fission reactors to catapult them into orbit. Massless energy powered by megawatt-scale fission reactors. The US Navy uses electromagnetic launch systems to launch fighter jets from their aircraft carriers. Obviously, for lunar orbit insertion, the velocities would need to be far higher. The delta V required to launch to low lunar orbit is 1,634 meters per second, much lower than what would be needed for low Earth orbit. To build such a system would require a substantial amount of power, likely a nuclear fission reactor plus a rail track system several kilometers long. Energy would be stored in capacitors and released during launch, which would only take a few seconds. Both a Lockheed Martin FSP reactor or an Antares micronuclear reactor have sufficient power to launch 1,000 kilos of lunar-derived water into low lunar orbit once a day, with plenty of margin, especially the higher-powered Antares reactor. Artemis Base Camp. After the initial landings on the Moon, NASA wants to establish a more permanent settlement called the Artemis Base Camp. It's likely to be established somewhere near the South Pole, with nearby water ice deposits and plenty of sunlight is available. Realistically, this isn't going to happen until the 2030s. One possible location will be the Shackleton crater region. The Shackleton Connecting Ridge is one of the best places for solar panels due to the sun being visible 354 days per year. This location is also near permanently shadowed regions which have high scientific value and likely contain large amounts of lunar water ice. Stationing a base camp here would also allow long-term habitation due to cheap solar power available most of the year. This would remove the need for expensive and heavy battery storage to survive the lunar night. The Shackleton Connecting Ridge is also a prime candidate for the Artemis 3 crewed landing, likely in 2028 or later. The key components needed for an Artemis base camp would be lunar rovers, unpressurized and ideally pressurized vehicles. 3 American companies are working on unpressurized vehicles for NASA, and JAXA, in cooperation with Toyota, are providing a pressurized vehicle as their contribution to the Artemis program. Surface habitats will be needed and power systems for life support, charging lunar rovers and powering scientific equipment. In situ resource utilization is also likely to be part of these base plans. In the early phases of the base, it's not expected to be permanently manned. More robust power and infrastructure, including landing pads, refueling stations and local resource extraction, plus enhanced radiation shielding, would be needed to support safe and reliable continuous habitation. To quote from the Lockheed Martin novella, "By far the busiest hub on the moon is around the South Pole. You remember the view from your lander as you arrived, burning the long arc of the landing trajectory as the base camp came into view, from the blackness of space to the blinding white light of the lunar surface. There, from the landing pad, you could see the sprawl of the Artemis base camp. The cluster of landing pads and spaceport infrastructure were bustling as you arrived. You could see some landers being loaded and others unloaded by support robots, and others being refueled so they could return to orbit. The Artemis base camp is some distance from the landing pads to avoid any ejector or debris from the landers escaping over the protective berms around the pads. Rovers crisscross the moon from South Pole to equator. You can see the solar panels glinting in the sunlight, with fission reactors in the distance, and power lines connecting them to their base camp facilities and habitation modules." Unquote. Upcoming events. Artemis 2 is due to launch in the next few years. This will be a circumnavigation of the moon without a landing. Artemis 3 will be the first crewed landing on the moon since the 1970s. It's unlikely to happen before 2028, as the Starship system, including in-orbit refueling, needs to be perfected and a demo mission to the moon needs to be completed successfully. Lockheed Martin are a key part of the Blue Origin national team, working on a human landing system. They are also involved in lunar power solutions such as the vertical solar panels, and are working on nuclear fission designs. Lockheed Martin developed a realistic virtual lunar base using the Unreal Engine gaming tool. Check out the Lockheed Martin video. I've linked to it in the video description to see a virtual tour of their lunar base. You'll get to see power stations, habitation modules and water ice harvesting. Okay, that's a wrap. Thanks for watching. Space News Live is on Saturday evening or Sunday morning depending where you watch from. I recap the videos I posted this week, answer questions, respond to comments and chat messages, cover any missed news and preview upcoming content. I'd love for you to join if you can. Be sure to like and subscribe so you'll see our upcoming videos. We make videos every week covering the space industry with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.